All right, today we're going to talk about conservation of energy. So let's just talk about the word conservation in general. Conservation of anything means the total amount does not change. We have the same total before as the same total after. Now, this is a topic that you should have already learned in previous science classes. When we talk about balancing chemical equations, the main idea is that we figure out how much matter or how much mass we have available with our initial reactants, and then the chemical reaction takes place. And then we're going to account for all of those same materials and the product side of that equation. They're going to look different, they're going to be organized differently, but all of that mass and all of that matter is still accounted for. So the total did not change before and after the chemical reaction. That is the main idea here. In this chapter, we are focusing on conservation of mechanical energy. And so we have stated before that we are going to be discussing specifically gravitational potential energy and kinetic energy. So it says that the law of conservation of energy means that the energy is neither created nor destroyed. It's just transformed from one form into another. So we are going to be looking at how the energy transitions between kinetic and potential energy. The total amount of energy is the same. That total amount does not change, okay? So here I have a drawing of what we're going to call a roller coaster, and we are going to start off at the top of the first hill of this roller coaster. So we should know from common sense that on our roller coasters in real life, the first hill is always the biggest hill. Now, conceptually, I'd love for you to just instinctively know that if we started with the shorter hill, then we wouldn't be able to make it up the next hill, right? We wouldn't be able to finish that ride. So that's kind of what our life experience and common sense tells us. But what I want you to understand in terms of the vocabulary and in terms of the math behind that, the first hill has to be the biggest hill because this is what's going to establish the total amount of energy that is available in order for you to have enough energy to finish the roller coaster. You have to start with the biggest hill because that provides the amount of energy that you have to use to make it through the rest of that roller coaster. So that's why we can't start with the shortest hill. We won't have enough energy, okay? So here we are going to start with our roller coaster at the top of the hill. And let me just remind you, our total mechanical energy, which is sometimes written as TME, not time, but TME. Here I have it really more of mechanical energy with the subscript of the word total. But this is the sum of PE plus KE. So my total mechanical energy is going to be adding my potential energy. And so let's just review real quick. Potential energy is calculated mass times gravity times height. So this height right here is what determines how much potential energy the roller coaster has to start the ride. Our kinetic energy is going to be calculated using the equation 1/2 of mass times velocity squared. And so we're going to say that at this absolute highest point for just a brief moment, my object is going to be at rest when it reaches the highest point. So here we're going to have a kinetic energy of 0 because we have no speed just for a moment when we're at the absolute highest possible point. So we are all potential, no kinetic. So if we say that total mechanical energy is the sum of these two energies, then I'm going to add these two values up and I get 50 joules. So this is how much mechanical energy we're going to have at all the different locations on our roller coaster. When our roller coaster reaches this point right here, conceptually, just main idea, I need you to know that we have a lesser height, so we're going to have less potential energy, okay? So conceptually speaking, we should understand that. Conceptually speaking, we should also understand that my object is now moving. So we went from no velocity, no kinetic energy, to some velocity. So now we are going to have some amount of kinetic energy. So right off the bat, we're going to have a transition between potential and kinetic. Both of these values are going to change. If we have a lesser height, we're going to have some amount of potential energy less than what we started. For argument's sake, let's just say that we've done the math and that comes out to 15 joules. So if I have 15 joules of potential energy, but I started with 50, well, what happened to the remaining energy? Well, that remaining energy was transformed into kinetic energy because now my object is moving. My object should be moving faster the farther down the hill. And so this is maybe common sense from life experience. Maybe we remember that we have that gravitational acceleration rate of 9.8 meters per second squared. And so it's just going to get exponentially faster and greater kinetic energy as it goes farther down the hill. So we don't have enough information to calculate the potential energy right now. In future word problems, we're probably going to tell you what that height is, and you're going to have to go and use mass times gravity times height to determine that it's 15. But for right now, we're going to say it's 15. So what if I wanted to know how much kinetic energy do we have? Remember, these two values have to add up to our total of 50. So if I am a person that really likes using the equations, if I like that concrete approach to solving things, my formula is going to tell me that my total mechanical energy is PE plus KE. So I have a total energy of 50. At this location, I have a PE of 15, and my kinetic energy would be my unknown. So mathematically, I'm going to subtract 15 over. 50 minus 15 is 35. So I'm going to have 35 joules of kinetic energy. Now, some of you may be thinking, I could just do that in my head. It's 50 minus 15. Yes, it is. But for those who like that concrete formula to fall back on, the formula is going to work itself out where you're essentially doing 50 minus 15, okay? So now, if I just go back and double check my math work, my total mechanical energy is the sum of these two energies, and that, once again, is indeed going to be 50, okay? Now, how are the word problems going to look when it's your turn to do the math work? That's going to vary. We might tell you what the potential energy is and just, hey, what is the kinetic? We might give you the height and ask you, what is the kinetic energy? Are you going to comprehend that you're going to be using your total energy equation and just calculate what that potential energy value is? So this is the higher level thinking that's going to be required of you. So when our roller coaster gets to the ground, when it gets to that lowest possible position, we are going to say that here we have a height of 0. We can't go any lower than this. We're going to call this quote unquote ground level. And so if we have a height of 0, then when I go to substitute my numbers in, that means my P equals mgh is going to calculate to 0. Conceptually speaking, when we are at the absolute lowest possible physical position, this will be a potential energy of 0. So we went from having 50 joules of potential energy at the top of the hill to no energy at the bottom of the hill. Again, energy is not created nor destroyed. It was just transformed. What did it transform into? Oh, it all transformed into kinetic energy. So down here, I have 50 joules of kinetic energy. Why? Because my total energy does not change. Because if I add this up, I still get a total of 50. Okay? So this is the main idea behind conservation of energy. Some of the questions that you're going to see will be pretty simple and straightforward. Most of the questions, though, we're going to maybe ask you for the velocity. And so you're going to have to figure out, oh, now that I know it's 50 joules of kinetic energy, I can use the kinetic energy equation to solve for the velocity. So it's your ability to understand big picture what happened to the energy, how did it move around, and then go back and use those individual equations to fill in those missing values along the way, or to understand that I'm going to take my kinetic energy and I'm going to expand that into the 1/2 mv squared so that I can actually solve for the velocity that they want. Okay, so higher level thinking needed to actually execute the problems, but we're just addressing the main ideas right now. Now, there's another thing that I want to address with you. We are going to often have our objects move to various locations, and if the question is asking you for some sort of connection or relationship between our energy here at the absolute highest point and our energy here at the absolute lowest point, I want you to be able to quickly interpret what that's going to look like. Now, as a general rule, conservation of anything means, let's do it this way. The total before is equal to the total after, and we've seen something like this before in this class. So since my total is going to be the sum of my energies, I'm going to have potential energy initial, and I'm going to have kinetic energy initial, and those two values are going to add up in order to give me my initial total energy. At the same time, I'm going to have a final potential energy, and I'm going to have a final kinetic energy, and those two values are going to be added up in order to give me my total after. Now, if I tell you that I specifically want you to calculate something that involves taking my object from the absolute highest point where my kinetic energy value is 0, when I go to substitute my numbers, this KE initial has a value of 0. And so that means that the whole value is simply going to go away. It's just going to fall off from my equation. So that means that on the initial side, I'm really going to have just my PE initial. Now, if I tell you that we are going to make that object later end up on the absolute lowest point or the ground where we have all kinetic energy, that means we have a potential energy of 0. So on the final side, this is the value that is 0, which is essentially going to go away from my equation, and I'm left with just that final kinetic energy. So I want you to recognize this as a shortcut. If we know we're going from the absolute highest point to the absolute lowest point, it's simply going to be the potential energy at the top, or the initial potential energy, is equal to the kinetic energy at the bottom, or the final kinetic energy. Now, this is only a shortcut when we're going from the absolute highest possible position to the absolute lowest possible position. That's how we end up with those values of 0, okay? But if that's the case, here is the equation that we're ultimately going to use. Now, for future questions, do you know that this is the main idea, main relationship for all locations on the roller coaster? But if we understand that we're going from the highest point to the lowest point, can you shortcut to this? Now, there will be some questions that you will have where you are not going to have enough information to calculate your potential energy or to calculate your kinetic energy. But that's okay. Maybe we're asking you for the height, so you're really solving for h. Maybe we're asking you for the velocity, so you're really solving for v. I need you to understand the relationship. I expect that if needed, you could take this and expand that out so that you're doing mass times gravity times that initial height. I expect you to be able to expand this to 1/2 mv squared, where that's going to be the final velocity that we're going to be plugging in. And so you might just want to write your equation like this. Now, just a heads up, there will be questions in the future where you must use this version of the equation. Otherwise, it will be mathematically impossible for you to answer the question, okay? So your ability to think critically, can you connect the dots between what you know and what they are asking for? What is the relationship between the different variables? So you can't just look at the equation, pick a formula, and go. You have to really understand what the vocabulary means. You have to understand the connection between the different variables conceptually based off of the situation in order to determine what that final formula should look like that you're going to ultimately plug your numbers in and solve for. Now, there's one last thing that we have not addressed yet, and that's what this red box here is hiding from us. So let's go ahead and open up this box. It says some energy may be lost to heat from friction. If you have a question where we are starting off at the highest point and we have a potential energy of 50 joules, but what if we get to the ground and we don't have 50 joules of kinetic energy? What if instead of 50 joules, we have 45 joules? That doesn't seem to follow the idea that the total mechanical energy is conserved. All right, so here's an important piece I need you to understand. What we've discussed so far has been conceptually. Theoretically speaking, all of that energy is transitioned from potential to kinetic. If we are on a frictionless surface, that is actually what really happens. But in real life, in the physical world, whenever this roller coaster goes down the hill, friction is present. So we've reviewed friction before. Again, put your hands together and rub real fast back and forth. That is friction. Friction generates heat. Heat is a form of energy. Remember, we talked about energy being present in lots of different forms. So heat is a form of energy. So if you have a question where friction is present, now as my object moves down the hill, some of that energy is transitioned into thermal energy. And so by the time my object reaches the ground, some of that energy has been removed from this mechanical system. And so we're left with 45 joules. So the question's probably going to ask what happened to the missing 5 joules. Maybe it's going to say that we lost energy. Well, we technically didn't lose it. It was just transformed into thermal energy. So it's not going to show up in the form of kinetic energy, okay? So you are going to have to understand most of our situations are going to be frictionless. So we're going to be theoretical. We're going to have all of that energy transferred into kinetic. But if friction is present, or if you have a question where you notice that we started with 50, now we only have 45, what happened to the rest of the energy? It must have been transformed into heat. Look back and see, yep, I'm sure you're going to find that friction was indeed present in that problem.